Okay, now that we have an idea of the differences, we're using a paired sample t-test and instances where that will allow us to address the questions we're interested in more accurately. Let's take a look at doing some sample problems. Similar to what we looked at with the independent t-test, we're going to be solving a problem using a critical value approach. We're going to solve a problem using the p-value approach and using StatsCrunch, and then we're going to look at doing the confidence interval, both with hand computations and with StatsCrunch. So the problem we're going to work with here is going to be practice problem number 17. It's on 469 in your book. And here we're going to be working with some data that we have regarding the box office success of two different Harry Potter movies. So we're told to use a significance level of 0.05, and we're testing the claim here that Harry Potter and the Half-Blood Prince did better at the box office than Harry Potter and the Order of the Phoenix. So, again, walking through these steps, it should be very familiar for you by now. We need to check the requirements. So first of all, what are the requirements for a dependent t-test? What do I have to have before I can do a dependent t-test? Stuff with it. List out these criteria. Well, we're going to have a simple random sample as always. Here we have to have our samples that are paired. That makes it the dependent t-test. And here we need to have, once again, either an n greater than 30, or we need to know that both samples come from populations that are normally distributed. So we're looking here, simple random sample. Yes, our samples are paired because we're choosing to look at them together in this particular situation because we're pairing the Harry Potter movies together within a group. And when we're looking at this, we do not have an n greater than 30. However, both samples, we're told, can be assumed that they are coming from a population that is normal. So, requirements. And so now we're ready to proceed on and look at our next step. So here we need to be looking at identifying the two different claims that we'll be working with and putting them in the symbolic form. Now, this is going to be different than what we've seen with the independent t-test. So here we're going to be putting our hypotheses in terms of mu d. This represents the mean value of the differences, the d, for the population of all matched pairs. So we're going to be solving, instead of mu1 and mu2, here we're going to be looking at mu d. So in this particular example we're looking at, here's your data set. I've kind of brought it up for you here on the screen. You can see we have the days of release here. So we have them for the Phoenix going across the top, and then Prince comes second. And then the bottom column I've added on is the D value. Okay, so that is the D. D is going to be the difference between those two. So D for day one of release is going to be 44.2 minus 58.2. Okay, so we're taking the value for the Phoenix, and we're subtracting the value from the Half-Blood Prince, and that will give us the difference, the D, for the day one release. So if we do the calculations, we get negative 14. So our D for day one of release is negative 14. When we're looking at our mu of D, that is going to be all of those values summed up from the difference summed up across and gotten the mean of. Okay, so that's what we're going to be looking at, is the mu of D would be all of these values. Now, if we're looking at this and thinking our way through solving this problem and setting this up, the first step is thinking about what would happen if there was no difference between the Phoenix and the Prince. What would be the value of mu D? So take a moment and pause and think through this, because you're going to be able to solve this in your homeworks and the exams. If the Phoenix and the Prince, if there was no difference between them in their box office profits over the first 10 days, what would mu D equal? Well, it's going to equal 0. Okay, so because it would all even out, right? So that's going to be our top one up there is mu D equals 0. Now we have to look at the symbolic form that must be true when the original claim is false. Here we're looking for the cues from the way the problem is worded. So here we're being told that we're looking at testing the claim that Half-Blood Prince did better at the box office than the Phoenix. So if Prince did better than Phoenix at the box office, then would mu D be less than 0 or greater than 0? looking at how these numbers are ordered. And keep in mind when you're doing the dependent t-test, the order in which the values are put matters. So you can't be swapping them back and forth here. So if the half-blood prince did better than the phoenix across the board, would mu d be less than 0, i.e. negatives, or would it be greater than 0? Well, it's going to be less than 0, okay, because you'd have all these would be negatives at the bottom, just like we saw with the one example that was negative 14, right? So there are two different claims specified out. And if you need to go back and watch that again to make sure you follow how you extrapolate from the problem what your different hypotheses are going to be. And of course, we put in terms of a hypothesis, then we have our null, which is going to be mu d equals 0, and our alternative is going to be mu d is less than 0. So now that we have that, what's going to be the next step that I need to do? So I've got into my hypothesis formula. What do I need to do next? Well, I'm going to need to identify the specified alpha. So the alpha for this particular problem is going to be what? It's going to be 0.05. They've given it with our significance level. So we have that. Now we're moving on to identifying the relevant test statistic. To do that, we need to look once again at this table. So looking at this table, we can see that we're solving for a mu, clearly. So that means we're looking for a mean. We're using either a t or a z distribution. And then looking at the parameters for our problem, here we are working with, again, a sigma not being known. Okay, so we have no reports of a sigma for the population. And we do know that we are told that the populations are normally distributed. So that means we are going to be solving for a t. Okay, now that I've got my relevant test statistic, what's my next step? What's the next things I need to do to solve this problem? I'm going to need to calculate my test statistics. So going through and looking at that, here is the formula we use for hand calculating your t obtained value. So you're going to take your d bar, right, which is the representation, okay, and so you're going to take that and you're going to subtract it from the mu d, okay. So here we see our d bar, and we see that this goes all the way across, because it's negative 1.57. So those are all my different values all the way across, both positives and negatives being included into the formula. So that gives me negative 1.57. Now my S of D here, you can see the formula for calculating it by hand. However, you can also get that with summary statistics. We'll look at that in just a minute. And keep in mind, when you look here at these numbers, you're going to see that we're plugging in our value of d, and we're working with the assumption that mu d equals 0, because that was with the null. So remember, we're testing the null, so thus we use our mu d minus 0. So that's where that comes from. Okay? And we plug in our values, and we get a negative 1.08. So that is my t obtained. And now I need to have what? I've got to determine my critical value that I'm going to do my comparison with. So, determining a critical value. What pieces of information are required to locate the critical value? What do we need whenever we're locating our critical value in the t-distribution table? Degrees of freedom. We're going to need to know our alpha, and we're going to need to know if it's a left, right, or a two-tail test. So, if we're looking at the degrees of freedom, this is going to be, here is going to be n minus 1. So that's going to be 9. We've already found that our alpha is 0.05. And when we're looking at this test, we can see that it is a left tail because it is the less than symbol. Remember again about paying attention to the language in your hypotheses to be able to interpret from that what type of tail test you have. So make sure you've got that clearly in your notes. We have that covered in the videos for the independent t-test. So now that I've got that, take that information and go look it up in your book in the t-distribution table and locate your t-critical going to be what? Take a few moments and look that up. Pause the video while you do that so you can make sure you're locating the right values correctly. It's going to be 1.833, but it is a left one-tailed test, so the value is going to be negative 1.833. So here is again, you have to pay attention to thinking your way through the problem to make appropriate adjustments. So now that we have our t-critical value of negative 1.833, and we've got our t obtained, what is our next step here? We're going to graph our distribution here. So, whiteboard, you should be getting something that looks like this. So you have your distribution, and we diagram on our t-critical value here of negative 1.833. Now, let's think our way through here for a moment. What is going to be the rejection region? What region am I going to shade for, we'll say for blue, showing that that is the area, if my t obtained falls within it, that I reject the null hypothesis, and what area is going to represent the failing to reject the null. So take a moment and put that into your figures yourself, because again, you should be working through these problems with me and putting them into your notes as a template for how to solve this type of problem. And you're going to look at this, so it's going to be to the left of it, right, because I'm solving a left tail test, okay? So it's going to be rejecting my null if my value falls to the left of my t-critical value, and I'm going to fail to reject the null if the value falls to the right of it. So now I've got mark on my t obtained. So I've got negative 1.08 for my t obtained. Where is that going to go in this figure? It's going to go here. So here is my t obtained, negative 1.08. I now have it all graphed out. And my next step is I need to assess the rejection region. So I'm going to reject my null if the test statistic is within the rejection region, and I'm going to fail to reject the null if the test statistic is not within the rejection region. So if we're looking at this, where does my t obtained fall? We're going to fail to reject the null. It's falling within the fail to reject the null region. So now we're restating our decision in non-technical terms to address the original claims that we've specified out here. And we have our figure here to the left, to our flowchart. I'm kind of a little unpleased with how the wording in this flowchart is set up, so I don't think it's as clear as I would like it to be. So I have added on here for you cues for you to add into your own flowchart. So looking at this really briefly, if you're looking at whether or not the claim contains the condition of equality, I think that language is a little bit unclear, so I've just gone ahead and labeled for you that what they're looking at there is if you're doing an independent sample t-test. So if you're doing an independent samples t-test, you word it one way. And if it's a dependent samples t-test, you're going to word it a different way. So I strongly suggest that you take that flowchart, you should print that off from Blackboard so you have it yourself, and then add these two notes into it to help you more effectively use that flowchart. So looking at that flowchart, we did not reject the null, so we failed to reject the null. So that means that if looking at that, we're going to have this is our wording for our restating our decision. There is not sufficient sample evidence to support the claim that the Half-Blood Prince did better at the box office. So this concludes doing a dependent t-test or critical value approach.